Hello everyone, I am going to present a 3D visualization of Superscalar Processor Architecture. To make this complex inner working easier to understand, we have modeled the CPU components in a zero gravity anti-gravity space. Traditional block diagram often fail to capture the dynamic simultaneous nature of modern processors by letting the components float freely, separated by space but connected through glowing energy pathways which represent our data buses. We get a much clearer picture of exactly how instructions flow, split, execute, and coverage in a truly parallel system. Step 1. The front end. Our journey starts at the very top of architecture. You can see glowing particles entering the system. These are our program instructions. They first enter the instruction fetch unit IFU. The IFU's job is to pull the next instruction from instruction catch. From the IFU, the instructions flow down the energy pathway into the instruction decode unit IDU. Here the raw binary instructions are decoded into micro operations. The processor figures out exactly what operations need to be done, whether it's math calculations or memory load or a branch. At this stage, everything is still happening in strict sequential program order. Step 2. Dynamic scheduling and EQ. Next, the decoded instruction move into the heart of processor's dynamic execution engine, the scheduler. In our model, this is visualized as rotating hub, symbolizing how it continuously assesses and distributes workloads. Because this is a superscalar processor, the scheduler doesn't just send one instruction at a time. It intelligently receives multiple instructions simultaneously into the reservation stations RS. The reservation stations act as waiting rooms. An instruction might be stuck here waiting for the data from a previous calculation to finish. As soon as its data dependencies are met, the reservation station fires the instruction off to the execution units. This is where the processor breaks away from strict program order and begins executing instruction out of order to maximize efficiency. Step 3. Execution and data sharing. Now we reach the core of our parallelism. Below the reservation stations, you see multiple execution units glowing and working at the same time. We have three ALUs, arithmetic logic units, handling basic integer math and logic. We have the FPU, floating point unit, dealing with complex decimal calculations. And we have the LSU, load store unit, reading from and writing to memory. Notice the glowing particle streams shooting down into all of them simultaneously. This is the definition of instruction level parallelism, ILP. Multiple instructions are physically being processed into the exact same clock cycle across different units. Off to the side, you will notice the register file. It is connected to all execution units via light beams. As the ALUs and FPU calculate results, they consistently read and write data back to this register file, sharing information instantly between parallel pipelines. Step 4. The backend and conclusion. Because our execution units are finishing tasks out of order, for example, a simple ALU addition might finish much faster than a complex FPU division. We need a way to restore the original program order. Otherwise, our software would less or execute incorrectly. That is the job of ROB or reorder buffer. All the execution units are funneled their finished results here. The ROV catches the completed instructions, sorts them back into the exact order the programmer originally wrote them, the safely retires them. Finally, the results move to write back unit WBU, which officially commits the data to memory or architectural registers and shoots the finished data out of bottom of the system. To conclude, what you are seeing is incredibly chaotic, out of order, highly parallel execution of modern superscalar processor, elegantly sorted back into perfect sequential order by time